in previous lecture we looked at some regular packing and also saw that there are some non-regular packing. Of course, the regular packing are not something that you would actually expect in a real material. What you would expect is a non-regular arrangement, and for that we also saw that we can get relations something like number of particles per unit bulk volume and number of particle contacts per unit volume. So, these were obtained directly from regular structure, but then these can also be extended, the knowledge can be extended to non-regular structure. And even before I proceed further, we have seen that there are two non-regular packing we looked at, was loose random packing and dense random packing. However, if I tell you that for a sub-micron alumina, the rho that you get is of the order of 0.3. So, what would your thoughts be? We said that usually you should get, when you have not tapped it, then 0.6 for the loose random packing. When you have tapped it, then it should be dense random packing close to 0.64. Then why are we getting for sub-micron alumina powders something like rho? This is again relative density. So, relative density equal to 0.3. Then you have to remember that when the particle size reduces, agglomeration tendency increases. So, this is because of agglomeration. So, agglomeration can change these values, because in agglomeration particles will come together and they will not be so tightly packed, and each agglomerate will itself be very loosely packed, and it will, even if you get them to pack later on with a dense random packing, each of the agglomerate itself has very low density, and so the average relative density would be very poor. So, now having said that, now let us again look at the NC value, that is the number of particle contacts per unit volume that we obtained. So, we saw that these are NP is equal to 6 by pi d cube by Pf. Now, here everything we know can be obtained for even a non-regular packing. So, this equation will be retained even when we are talking about non-regular structure. However, coordination number is not something that we can obtain for a non-regular structure very easily, and some researchers have shown that coordination number can actually be given by under certain conditions like this. So, this is now a equation or a relation that we can again utilize even for non-regular packing. So, this is the coordination number, and if we have the coordination number, then we can also obtain number of contact points per unit volume, which used coordination number by 2, and therefore, this will come out to 3 by Pf times 1 minus Pf cube. So, this is Cn by 2 times Np, and over here you would get the form of the relation would be like this. So, this is equal to Cn by 2 times Np. Actually, there is no cube over here. So, this should be 3 Pf by pi. So, this is actually d cube, not 1 minus Pf cube. So, this is 3 Pf by d cube, pi gets cancelled, and you also have this 1 minus Pf factor. So, this is the relation for that is valid for non-regular structure. Here, because we do not know the coordination number, so we obtained this coordination, the relation for coordination number was obtained by some researchers, and they have given it like this in terms of Pf, which we can calculate or we can obtain, and then we have Np and Nc. These are some important parameters to understand how much densification is taking place. So, this is valid for non-regular structures. So, now that we have introduced some important parameters which will be useful when we talk about densification. So, now let us get to next step, where we so far we used just one mono-sized spherical particles. Next we want to move on to a pi-modal distribution of particles and see how much density or how much packing fraction we can get. Once you have obtained the packing fraction, then you know we can obtain other important parameters like number of particles per unit volume and number of contacts per unit volume. So, now we will move to the next stage, which is to find out what will be the packing fraction, or at least the apparent packing fraction, when you have bimodal distribution. What do you mean by the bimodal distribution? Ideally, it would mean that you have two distinct diameter and a spread around it. So, something like this, if I were to draw it, so here you have diameter and here you have frequency. So, this is one diameter, this is another diameter, but in our case we are making things even more simpler, and we are saying we have only particles of this diameter and particles of this diameter. We are not considering even a distribution. We have particles only of exactly two diameters, and to further make things tractable, or so that we can formulate relations around it, we will assume that d fine is less than, or let us say d coarse is greater than 10 times of d fine. So, our coarse diameter particles are at least 10 times that of fine sized particles, and we will see where this fits in. So, now we have to put it like this. We have two particles, let us say one d, we will call d coarse, and another small particle we will call d fine. And if it is getting arranged in some particular arrangement, then we will say assume that it has a packing fraction which is constant given by PFC, and when this is getting arranged in some fashion, we will assume it is constant, meaning it is not changing from one point to another, and this is PF fine. So, now that we have here, we will have two extreme cases. So, let me write it. One, when we add small particles to coarse particles, meaning coarse particles are already arranged or already sitting inside a jar, and you pour in fine particles. So, okay, to be again consistent, let me use fine instead of small. So, add fine particles to coarse particles. Now, what is happening over here? So, again the way I have drawn it, it is not really representative. Let me make it even smaller. In fact, it will even be smaller, and therefore, what we have is something like this. So, let us say there are particles arranged, there will always be some tetrahedral or triangular pore kind of structure formed over here, and this like I said, the drawing that I have shown here is a little exaggerated. The particle size would be even smaller than this. So, let us say this is our small particle size. So, this is our and this is our coarse particles. What we see is that when you are adding the fine particles to the coarse particles, the fine particles are taking the pores they are not displacing the larger particles. It means the overall volume, the empty volume is getting reduced, or the pore volumes is getting reduced, and therefore the packing fraction must overall increase. Now let us say we have let us define some of the terms. So total volume is equal to Vt, meaning it includes the volume by the large particles, by the coarse particles, the coarse particles, the fine particles, and the pore. So this is fine plus coarse plus pores. Everything included is our total volume. Then we have mass of the coarse particle, meaning we are now only considering the masses of the coarse particle. Similarly, you will have mass for the fine particles, so you will have masses of the fine particle, and corresponding to that there will be a Vc corresponding to that, meaning volume of the coarse particles. Corresponding to this there will be a fine particle volume, which is Vf. And remember, Vc plus Vf is not equal to 1 because there is still some pores. So Vc plus Vf plus V pore is equal to 1 or 2 V total, not 1 here, we are not looking at ratio. So Vc plus Vf plus V pore is equal to Vt. And let me also define true density, meaning what is the bulk density. So we will use the term rho T, and therefore if you were to take MC by Vc, it will be equal to rho T, true density, because we are looking only at the masses of the coarse particle and only the volume occupied by the coarse particle. So this is the true density. If we take MF by Vf, that will be the true density, because we are talking about masses of the fine particles and only the volume taken by the fine particles. However, if we take MC by Vt, then that is low density, lower than rho T, because now we are taking about whole volume, which includes, if there is no fine particles, then it includes the coarse particle plus the pores between the coarse particles, that volume. So mass by Vt, so that density is smaller, and that will be, you can say, the rho C, or the coarse density. Now let us move on and try to look at how to get the apparent density for this. So the apparent density can be, what do we mean by apparent density? Meaning the total mass that we have for the coarse and the fine, and the total volume, which is volume coarse, volume fine plus volume pore. We are not dividing it by only the volume core plus volume fine, because that will be equal to the true density. We want average or relative density with respect to the bulk density, because pores have got included, and that is what is making a lot of difference. So this is what we are interested in, which is going to give us the rho apparent, and this will be equal to we can write it as MC by Vc times Vc by Vt plus MF by Vf into Vf by Vt. So we have just multiplied it by Vc by Vc, this one by multiplied by Vf by Vf. So MF by Vf, we know what it is rho true. MC by Vc, we know what it is rho true, and Vc by Vt, we know it is equal to, okay, we will let it be like this for now. So we have rho true in both of them, and I have shortened from apparent to APP, or we will even make it rho A. So this is rho A by rho T times Vc by Vt plus Vf by Vt, but again here what we will do is we will take Vf or multiply it by Vt minus Vc. You will see in a moment why we have done this. So we have multiplied it on both sides, Now Vc by Vt, what it is? It is nothing but packing fraction of course. We are looking at the volume taken by the coarse particles and the total volume. So, that is the packing fraction of coarse. Here we are looking at the volume taken by the fine particles and the pores that were available to them overall, which is Vt minus Vc. So, the overall pore that were available after taking away the coarse particles. So, this again represents Pf fine, and that is why we multiplied in the numerator and denominator by this quantity Vt minus Vc. Now, over here we have again Vt minus Vc by Vt, which is equal to 1 minus Vc by Vt, and we know Vc by Vt is again Pfc. So, this becomes 1 minus Pf coarse. And what is this rho apparent by rho t? You can see that this can be written as, so this is mass by density. So, let us say this is mc plus mf, which will get cancelled anyhow, and this is by the Vt, this is again mc plus mf, but here we are only looking at the volume of coarse plus volume of fine. So, this translates to Vc plus Vf by Vt. Now, this is nothing but this is equal to our rho packing fraction apparent. This is, you can say, the overall average packing fraction of this material, because these are the volumes which have been occupied by the particles, but this was the total volume available. So, that is what represents the packing fraction. So, this is the apparent packing fraction. Times so we have now a relation for the apparent packing fraction when we have two particle size, two diameters. One is the coarse one and another one is fine one, and based on that we have a packing fraction apparent which is equal to, which can be given in terms of packing fraction coarse plus packing fraction fine times 1 minus packing fraction coarse. So, this is, if you put the values, for example, let us assume that both coarse and fine pack in FCC, kind of face centered cubic type of structure. Just for the sake of argument we are saying this, and therefore, if you put this value which is equal to 0.74. So, both packing fraction coarse and packing fraction fine will become 0.74, and when you put it over here you would see that packing fraction apparent is equal to 0.932. This is just one example. Here you could have any other arrangement for coarse and any other arrangement for fine. You could as well have this as loose random packing, coarse random packing, or both of them simple packing, or anything in between. You can just say, or you know, for example, from your experiment that your coarse particles get arranged and have a packing fraction of 0.4 and fine particles have a packing fraction of 0.35. So, you will again be able to put those values over here to get to or to understand what would be the overall packing fraction. So, that is one extreme case when we have added fine particles to the coarse particles. Now, next let us move to the other extreme, which is this time we will add the coarse particles to the fine particles. And why will it be different? You will see in a moment. It will be treated, or you will have to treat it differently. So, we will add coarse to fine. Okay. So, we are not saying, or basically what we are doing over here is that this time all the smaller particles are already arranged in somewhere, in some place. Okay. Now, you know that fine particles, the coarse particles cannot go in pores, right? They must displace. So that is the important part. They must displace. Earlier we did not have any displacement. Must displace fine particles. So that is what makes it different. Here here the coarse particles cannot get into the pores. They must displace the fine particles and then come over there. So for example, here we were drawing like this. Now let me say there is a big region like this, and when the coarse particle comes over here, it will take this region, and around it the fine particles would still exist. And so on. So again you can see that when we displace the fine particles by the coarse particles, there is an increase in the packing fraction, because in this region now whatever pores were there, they have disappeared. Now it has been displaced by a bulk material. Another difference here with respect to the previous case that we saw is that in the previous case we assumed that all the pores, because the fine particles are going into the pores, we assumed that all the pores would be taken by fine particles. But here we have a coarse particle displacing the fine particles. So we are not assuming that it will fill all the places, and therefore we will have to assume some fraction. So let us say Xc equal to Vc by Vt is the fraction of coarse particle in the overall volume, meaning this much fraction in the total volume has been replaced by the coarse particles. And another thing is that this is not equal to packing fraction of coarse. In the previous case where we assumed that the overall coarse volume were fully packed, the coarse particle were fully packed in the volume, then over there Vc by Vt would have meant packing fraction. But here some random places to begin with will be occupied by the coarse particles, and therefore that Vc by Vt does not represent packing fraction. So you must be aware that this is not packing fraction. This just represents a section or a fraction of the volume, of the total volume, which has been taken by coarse particles. So continuing with this, initially when Xc is equal to 0, we can say that V occupied by V total is equal to we saw that rho apparent by rho total is rho true is equivalent to saying V occupied by V total, and this would be equal to packing fraction fine, because initially we are saying Xc is equal to 0, which means there is no coarse particle, only fine particle. So if we are looking at the initial stage where Xc is equal to 0, then the packing fraction apparent, which is equal to V occupied by total volume, is equal to rho apparent by rho total is equal to packing fraction fine. Now this would also imply that rho apparent is equal to packing fraction fine times rho true. Now replace Xc fraction of volume by large particles. Okay, so this at this stage we had only fine particles. Now we are saying XC volume, which is Vc by Vt amount, is being replaced by large particles. So you can say that rho apparent will be equal to this will be increased by how much? Let me just put a line over here. We are replacing those regions by the large particles, which means whatever porosity there existed does not exist anymore. It is now a bulk material with bulk density. So it will increase by so this is the amount of pores that have been filled, and therefore this is the increase in the rho apparent. Another way we can also look at it in another way. So let me write it over here. I will keep the lower equation so that we can compare it with the new equation that we will obtain. The another way to look at it would be, let us say V occupied by V total is what we were looking at. So this is Vf plus Vc so initially when there were no coarse particles, this would have been V fine by to be again I was using small f, so let me continue with small f. So initially it would have been Vf by Vt, but now some of that region we said the Xc volume has been replaced by coarse particle. So that replacement is represented by this volume. So this is again the volume which has been occupied, Vc times 1 minus Pff. It is the amount of volume which has been replaced has the packing fraction 1. Initially we were counting it as packing fraction f. So the difference has been added 1 minus Pf times Vc, which is the volume which has been replaced, and therefore this represents again the rho apparent. V occupied by Vt is the rho apparent, and therefore we have rho we can say that Pfa is equal to Pf fine. So these two are equation, as you can see, are same. What all we are doing is taking rho t to the denominator, because rho t is common on both of them, and we are left with rho a by rho t, which is equal to Pf apparent, and therefore this becomes Pfa plus Xc 1 minus Pf fine. So this represents the apparent packing fraction when we are replacing the larger particle, the smaller particles by the larger particles. Finer particles have been moved. So when we move, when we do like this, that is there were some very fine particles, and in that we have replaced by a bulk. It's as good as a bulk, and here is the size. So these are the coarse particles. These have come in place of this region, and around it you still have those fine particles as we had earlier, and in that case you will get Pf apparent equal to this. And two main important difference between these are, one, over here you see that Xc is present, or Xc is a factor which is a variable. So we are looking at it as a function, or as a function of how much fraction has been replaced. You remember we said not all the region can be packed with coarse particle, unlike in the previous one. In the previous one the fine particles were going in the pores, and therefore we can easily say that all the pores are filled, and therefore there is a constant relation, meaning it is talking about the maximum, or the point where maximum packing has taken place. Coarse particles are completely packed and all the pores are packed by fine particles. It is representing that condition. We can even look for a condition where that is not the case, or where it is varying, where some amount of pores have been filled, then again some more amount of pores have been filled, and finally when all the pores have been filled. So, that will be the region, and we can also get a relation with variable amount of fine particles. But this inherently, this equation inherently has a XC, which shows how this relation varies with the fraction of the particles or the volume which have been exchanged by the coarse particles. So, that is, these are the two main differences. Next time what we will do is we will try to, or we will show how to plot this, not how to, basically how it will look like when you plot this as a function of coarse particles in the total volume or as a function of fine particles in the total volume. And we have to be careful when we make that plot. If you do it as a function of let us say volume by total volume, then it will be very different from what you should see when you draw it as a function of, let us say, volume of Vc by Vc plus Vf. Those two would be very different. So, we will look at that plot in the next lecture. So, we will come back on this slide. Thanks.